There we go. All right. All right, so I'm going to take this one out. And oh, also we have a computer science club now. Three students, basically rebooted the computer science club. Currently, we meet on Mondays and Wednesdays from 1:30 to 3 p.m. So if you are around on campus during that time, come, to room 321, same building, 321. That's where the computer science club is meeting. They talk about lead code problems and some other kind of fun stuff. So, alrighty. So we are now back to the normally scheduled program, and I think I sent out this announcement just as a reminder of what I should be talking about today. So the first one is the LDI instruction. Every time you see an instruction that you have not seen before or you have not used before, the best way to learn about that is the opcode table. And let me see, I got the opcode table here. All right, let me put this one here and look at the opcode table. All right, so this is the opcode table, and we want to know what LDI is doing. So we just have to scroll down a little bit until we see LDI, which is on row 22. So once again, on each row, there are four columns that are important. The last column describes in English words or in a phrase what the instruction does. So in this case, it says load constant value right after the opcode into a register. So what that means is when you look at the mnemonic, this is the mnemonic of LDI. So LDI is the name of the mnemonic. X is representing one of the four registers, A, B, C, or D. And then I, lowercase I, is representing what we call an immediate value. So an immediate value is basically the same thing as a const in C++. It is simply an expression that has to be resolvable at assemble time. Okay, so do we have any questions about that particular sentence? I has to be a value, an integer, that is resolvable at assemble time. The assembler has to be able to figure it out. Are there any questions about that particular statement? Okay, I'm not seeing any questions. All right, well, we can then proceed. So what I'll do next is I am going to bring up the assembler and just write a very short program to illustrate what LDI does. Okay, so all of this is going because this is a little bit more complex than what I want to do. So I have LDI register. Okay, let's say register C, and you can give it an expression, any expression that evaluates to an integer. So that means it doesn't have to be just a constant like 23. You can give it something like 23 plus 5 and then the whole thing times 2. Except that you can only specify the expression using a postfix notation. Did I talk about postfix in this class? I did? Okay, very good. So now we can give it a try, like exactly what I said, 23, 1 plus 2 times. So that is 2 times the sum of 23 plus 1, so the end result should be 48. And then we put a halt instruction right next to it, just so that the simulator, the processor, would basically stop on the second instruction. And we can now switch to the assemble tab and basically look at are we getting the correct bytes? So the opcode of the LDI instruction loading into register C is 6E itself. The 30 is representing the constant, the value that we want to copy to register C in this case. 30 means we have none of the ones and 3 of the 16s. So 3 times 16 is indeed 48. Does that explain why 48 in decimal is represented as 30 in hexadecimal? Is that okay? All right. All right, and then the halt instruction has a single opcode of 0, 1. So once again, I'm going to demonstrate how to load this program into the RAM of the processor, just so that you guys can kind of get used to the whole process because it's going to be something that is going to be useful in today's lab. So the way you do it is you go to the RAM file tab, go to File, click on Download, and then specify CSV. And I configure my browser to ask me where I downloaded to and also the file name. I will call it test.csv again. Since the file already exists, I have to click Replace, and there we go. Now I can switch to Logisim. So let me switch to Logisim. Reset it first, okay? So go to Simulate and then Reset Simulation because you want to start from the beginning. And then right-click on the RAM component, go to Load Image, and then specify the file that I want to load into RAM. In this case, it's test.csv. Click Open, and now we have the program in. Now, for something this simple, if you say, oh, instead of going through all that trouble, I'm just going to overtype these locations with the values, that works too. Not a problem, okay? I just want to illustrate the process of doing it using the tools. All right, so what we're going to do now is I'm going to single edge and trace the entire execution of this program. And throughout this process, I will also call out the different major steps of executing an instruction. And if you want to take notes, you probably want to kind of double check and make sure that your understanding of those important steps is as what I would describe in today's lecture. All right, so how do we get started here? When you get started, you always focus on the output of the ROM or what is directing the ROM in terms of the address of which location we look at. Because we just reset the entire thing, all the registers are zeroed. So that means the microcode pointer is also zeroed. And because the output of the microcode pointer is connected to the A port of ROM, so that means we are addressing location 000 in the ROM, and the content of that location is now output into the D port. So that's the first step. Second step, we check out what is active, what is being used, and how things are routed within the processor. So the first thing I typically check is the RAM component. The RAM component is indeed selected, which means it is active. LD is a 1, which means we are reading. And now the next two questions would be, who is connected to the A port and who is using the output from the D port? So those are two separate questions. First question first. The A port connects to the output of this multiplexer. This multiplexer has a select of 1, which means input 1 connects to the output. So now we have to track down input 1 of the multiplexer. And that one ends at the program counter. So we know the program counter is connected to the A port, and whatever the content of the program counter has is telling us which location of RAM we should be reading. So that answers the first question. The second question is, who is using the D port? The D port goes to many places, but since I have already talked about this in a previous class, I'm just going to shortcut the entire thing and say, well, look at the instruction register. The D port of the instruction register, which is the input to the register, connects to the D port of RAM, which is now in output mode. So that means the content at location 00 is now being presented to the input of the instruction register. The enable of the instruction register is also a 1, which means on the next rising edge, the instruction register will be updated to the content at location 00 of RAM. This particular step has a very special name, and what is it? This is called the something cycle of executing an instruction. And which cycle are we talking about? Starts with the F. The fetch cycle. Very good. Okay, this is the fetch cycle because we are grabbing content from RAM and put it into a register inside the processor, which is called the instruction register. This is called the fetch cycle. It is important to remember the name of these instruction cycles. Not because I'm going to test you on these things, it's too trivial for me to test in this class, but because at a 4-year university, there will be an upper division class that is the follow-up of this class, and they will care about the naming of the execution cycles. All right, so Control T is going to give me an edge, which means the clock is going to go from low to high in this case. Okay, let me do it one more time. There we go. So you can see how the clock going up is um, is creating the edge that we need so that the instruction register is now updated to the content of location 00 of RAM. So now the fetch cycle is completed. The falling edge is going to increment the microcode pointer, just like that. And now the rising edge this time is going to auto increment the program counter. And once again, the reason why we auto increment the program counter at this point is because location 00 is already utilized. The content is already sitting in the instruction register. There is no need for me to point to location 00 at this point. So the program counter advances to the next location. Is that okay? All right. All right, so now we're going to have a falling edge, and this particular falling edge also marks a very important part of executing an instruction. Which cycle are we talking about? It starts with a D. Dispatch. No, it's decode. Okay, so we are decoding the opcode now. Okay, so from the lab from Tuesday, okay, which asks, one particular question that relates to the decode process. What is going to happen in a decode cycle when you execute an instruction? It has to do with what is in the instruction register and how it is going to update the microcode pointer. So what's going to happen now? We have a 6E in the instruction register, and I just said that that 6E is going to somehow be utilized to update the microcode pointer. So what would be the content of the microcode pointer as soon as the falling edge happens? This has to do with the second question of the lab on Tuesday. I'll let you guys think about it a little bit as I drink my water. Any answers? Yep. Mm-hmm.
The 60 will go to the instruction, and then the multiplexer will combine the zeros and the instruction, and we will have 6E0, and then it will go to the microcode pointer.
Yep. So microcode pointer will update to 6E0, and then we'll be addressing the location 6E0 in ROM. That is correct. Very good. All right. It's amazing how much one cup of water can do. If you watch Initial D, the animation series, you'll go like, yeah, that cup of water does matter. And of course, tofu too. All right, so the mechanism here, I'll just explain it one more time, is the output of the instruction register is going through the tunnel that is called instruction, and it comes out from here. The bit 0 to bit 3 are all zeros, but bit 4 to bit 11, they all come from the instruction register, which is all up here. So as a result, the microcode pointer will have the most significant 8 bits coming from the instruction register, but the least significant 4 bits will be coming from just the constant of 0. So that means, you're going to see the 3 digits, the leftmost 2 digits will be coming from the instruction register, and then the rightmost digit in hexadecimal is just going to be 0. So Control T, and that's exactly what happens. No, I forgot. Okay, one more Control T. There we go. So the first Control T is to increment the program counter, which is now 0, 1. And then the second Control T is the falling edge, which is the actual decode, and that's why we are now at 6E0. So there, yeah, go ahead.
It's always going to be 0, right? Like the two leftmost.
You mean the least significant digit in hexadecimal?
Yeah.
After the decode process, yes. Immediately right after the decode, it's going to be a 0. but it's not guaranteed to be a 0 as we execute the microcode for a particular opcode. It's just that at this point in time, all the instructions that I'm supporting, they only require one slice in the microcode, and that's why we don't see that increment to like 6E1 or 6E2, because the instructions that I implement are very simple. All right, so that's a good question. So right now, there are a few things that are quite important because we can see that there are three things that are enabled, and most of those are actually visible within this range. So let me just scroll a little bit and point out which three things are active at this point. We can see that RAM is active because the chip select of RAM is a 1. We can see that the program counter is active because the enable is also a 1. We can also see something in the register bank is also about to update because the register input enable is also a 1. So there are three things that we need to pay attention this time because we have the program counter, the register bank, and also the RAM component. They are all active at this point. So as usual, I'm asking the question based on the RAM first. So we ask the question, who is connected to the A port so that we are now addressing the second byte or byte 0, 1 in this case. As it turns out, the multiplexer is still having a select of 1 like last time, and that connects to the program counter. We know that already. So the program counter is actually telling us where to read in RAM. We know we are reading because LD is a 1. So the second question is, who is paying attention to the D port of RAM? So now we click on the output from the D port of RAM. It goes to many places. So I will let you guys check out all of the other places and know that they do not matter. But the one that does matter is the connection here. So the output of the D port of RAM connects to input 0 of this multiplexer. The select of this multiplexer, which is under the gray dot, is a 0, which means input 0 connects to the output. And we also want to make sure that the multiplexer is indeed enabled. And we can see that because the register input enable is a 1, which also enables this multiplexer. So when we get into the the register bank, we can now see what is inside. This is the actual content of location 0, 1 in RAM, which is 30 in hexadecimal. It is presented to the D port of all registers. So register A, B, C, and D, they can all see this particular 0011, 0000. But only one of them has the enable being turned on because the decoder is doing its job of only outputting a single one to one of the 4 outputs, depending on the register input select pin, which is also 10 in this case. So as a result, register C is the only one that is going to update to 30 when I give it a rising edge. Are we doing okay so far with this analysis? Now, if some of you are thinking, Tag, you have gone through this many times, if this is starting to get to be really boring, well, congratulations. That is a good sign. It's a good sign if you say, Tag, can you stop explaining all of this stuff here? We know this already because you have said this many, many times already. That's actually a good thing because that means you are already absorbing the material. I'm just presenting the same thing over and over again. On the other hand, if you feel like this is the first time I talk about this, that may not be a good sign. In fact, I would say this is definitely not a good sign. Okay, if this is I'm not sure what you're talking about because this is the first time you mentioned this, that would not be a good sign. It means those people may need to go back and review from the earlier lectures. Okay. All right. So let me send it. Oh, there's one more thing because remember there was one more thing that is active. We have explored 2 of the 3 things that are active. One is RAM, one is the register bank. What was the third one? Starts with a P, the program counter. Okay, so the program counter also has its enable pin being a 1. So let's go ahead and check it out. So the program counter has its enable being a 1 because PCEN is a 1. So that means the program counter will also update on the rising edge. The question is, how is it going to be updated? So we track down the input to the program counter. It's coming out of a multiplexer. The select of the multiplexer is dark green, which means it's a 0. So that means input 0 of the multiplexer connects to the output of the multiplexer. Input 0, in return, connects to the output of the adder. The adder has a carry in of 1, and then the other input is coming from the program counter itself, which means we are just adding 1 to the program counter. So all this means is on the rising edge, the program counter will increment to 2. Okay, so that's the mechanism. The next question is, why are we incrementing the program counter? We're incrementing the program counter because on the rising edge, the content that the program counter is pointing to in RAM is going to be copied to register C in the register bank. So that particular function is already done. But the question is, why are we incrementing the program counter? If we do not increment the program counter, then the program counter will still be pointing to location 0, 1 at this point. So the next fetch cycle will mistakenly think that the next opcode is coming from location 0, 1, which would be incorrect. Because what is at location 0, 1 again? Okay, to understand what is at location 0, 1, the best tool to do that is the assembler. Go to the assemble tab. What is at location 0, 1? The 3, 0. What is the purpose of that 3, 0? Is that intended as an opcode? It's not intended as an opcode. It is intended as a constant value that we need to copy into register C. But by itself, it is not an opcode. It does not map to something that we want to do. It is simply something that we need to know to complete the LDI operation. So that means we do not want to execute 3, 0 as an opcode because the next opcode should be the halt instruction at location 0, 2. Is that okay? So this is why we need to auto-increment the program counter again, because if we do not, then we will basically mistakenly use location 0, 1 as the next opcode, which then will try to execute 3, 0 as an opcode, and that is not the intent of this program. Is that okay? All right, because it's important to understand the rationale behind the mechanism. It's like, why are we updating the program counter? So now we can expect two things to change on this screen. We can expect the output pin corresponding to the content of register C to update to 0011 0000. We can also expect the program counter to update to 01 on the rising edge. Okay, so let's go ahead and do the rising edge. Control T, and we can see how the program counter is now 02, and then the register C is now 0011, which is a 3, and then 0000, which is a 0. So it is 30 in hexadecimal. Are we good so far? Okay. So on the falling edge, because we are ready to do a falling edge right now, the microcode pointer would auto increment to 6E1, but because at the location 6E1, the output is going to have a 1 for bit 25. Bit 25 is one of the inputs of the OR gate, and then the OR gate connects to the reset of the microcode pointer. So as a result, we do get to location 6E1 for a very short amount of time, but then the register will reset back to 000. So effectively, you cannot see the microcode pointer changing to 6E1 because the amount of time is so short. So effectively, what we see as I do a Control T is it goes back to the fetch cycle because the microcode pointer is once again at 000. So this will fetch the halt instruction. So Control T fetches the halt instruction. You can see how the opcode of the halt instruction is now in the instruction register. Control T again is going to increment the microcode pointer. Control T again is going to increment the program counter. Control T again is going to decode the instruction register. The instruction register has 0, 1 in it right now. So that means the microcode pointer will update to it has the right digits, but at the wrong place. Two of the digits are now at the wrong place. 010, very good. Because a microcode pointer upon the decode cycle will basically just copy whatever we have in the instruction register for its most significant two digits. The least significant digit will become 0. So in this case, it becomes 010. Okay, so Control T, this is the decode, and we can now see that once we get to the location 010 in ROM, all the outputs of ROM become 0. What that effectively would do is to say the next, the rising edge is not going to do anything at all because all of the other components would only do something useful on the rising edge of the clock. And since everything is dark green now, so that means there won't be any rising edge here for, excuse me, I take it back. Okay, what I said was wrong. Um, the clock keeps going up and down, but the enables are all turned off. Okay, so nothing is enabled, so the rising edge would not matter to anything other than the microcode pointer itself. So the rising edge is not going to do anything. The falling edge is also not going to do anything. Why? Because the falling edge is going to update the microcode pointer, and I was using the update in double quotes because nothing is going to change. Why? The reason why that is the case is because the select of the multiplexer that feeds into the D part of the microcode pointer is dark green. It is a 0. Input 0 of the multiplexer is going to do the same thing as what we did in the decode cycle. It's going to decode the instruction register again. Did I change the instruction register since the last decode? Nope. So it's gonna decode the same 0, 1 opcode, and it's gonna change, quote unquote, change the microcode pointer to the same location of 0, 1, 0, and it's gonna be stuck in this loop forever. All right. So that is the entire trace of the execution of the LDI instruction followed by a halt instruction. I would advise all of you to do the same thing with other types of instructions. In today's lab, you would also use the LD instruction as well as the ST instruction. The lab does not require you to trace like what I just did, but I would advise you to set up a sample program so that you can actually trace it, so that one, you gain more familiarity with the processor. Two, you also get to understand exactly what is going on when you execute the LD and also the ST instructions. Is that okay so far? All right. So now what I'm going to do is to try to come up with a program to illustrate the use of those instructions, the ST and the LD instruction, and also how to use labels in this case. So let me change to the browser, change to the assembler, and erase the program that we have at this point. And we're going to start writing a new program. So let's just say that we want to write a program, write the code fragment that would increment the value at a certain location in RAM. So I'm going to even type this out and say the intent of this particular program. So I want to increment the content at one location of RAM. Okay. So what I need to do now is to use LDI so that I can store the address of the location that I want to increment into a register. So LDI register A is fine, whatever register you want to use. So right now I don't know exactly which location, so I'm going to guess location 8. Location 9 is one of the locations I can use. And then I would have a LD instruction, LDBA, so that I can go to location 9 and copy the content of location 9 to register B. Then I would increment register B and then store the incremented version of register B back to whatever location register A is pointing to, and that's the entire thing. And I would even go, explain what each line is doing. So the first line is simply saying A equals to 9. This is in C syntax. The second line is going to do something like this. B equals to the D reference of register A. And then the next one is, this one is easy. B is just B plus 1. We're incrementing B. And then the second to the last instruction is the reverse of the second instruction, which is wherever A is pointing to, let's update it again with the value of register B. And then the halt instruction is just, we're done here. All right? So do we have any questions about these instructions, particularly about the C notation that is describing what each instruction is attempting to do? So we're good here? All right. So I'm going to fast track and just run the program, without single edge, without single edging through the LD or the ST instruction. But I would advise you to do that yourself as an exercise, okay, just to practice how to do this over the weekend. So we go to RAM file and go to File, Download, CSV, and this time we'll give it a name. This time I'll name it as increment or inc.csv. Switch back to the Logisim, reset simulation, go to the RAM component, right click, load image, and specify the name of increment.csv. And now we got the program, and we can go ahead and just run all the way to the end here. So we can use window and simulate and make sure that the tick frequency is reasonably high. 32 hertz is okay. Okay, it will get it done in probably maybe 1 or 2 seconds, and yet you can still see what's going on. And before I enable the tick, let's find out where is location 9. This is location 8. This is location 9. So we're expecting this location to go from 0, 0 to 0, 1. Now, if this is too boring for you, you can actually go ahead and inject a value first and then see it just increment by 1. Okay, so let me go ahead and do that. Okay, so we'll change this location to AD for no particular reason. Okay, for no particular reason, I'm just initializing that location to AD. So now, after the increment, it becomes AE, exactly. Okay, so now we're going to run the program. If you prefer to single clock through the entire thing, you can just keep typing Control T on the keyboard. But I'm going to kind of use the ticks, auto ticking, so that there we go. So now it's all done, and you can see how that location is now changed to AE. We also know the program is done because the halt pin now has a value of 1. Okay, so now is a good time to stop the simulation. So we just have to uncheck, ticks enabled, and that's the effect of the program. Are we okay with this program? Are there any questions regarding the use of the LD instruction, not the LDI, but the LD instruction versus the ST instruction? They just look kind of awkward, but they do what the comment in the program says they would do. Let me switch back to the assembler, which is, where did I put the assembler? There we go. And we switch back to the source, which is where you can find the comment. All right, so the next question is, why did I choose location 9? Well, that was just a guesstimate, because I cannot choose a location that corresponds to the program itself, because otherwise the program will corrupt itself, right? And we certainly do not want that. There was a time in the history of computer science or programming when people do all kinds of tricky things like self-modifying code. Okay, so what do you think self-modifying code do? As the name implies, the program would update the locations and change its own opcode or constants. Why would people do something like that? Because there are shortcuts, okay, to make programs slightly more efficient by using self-modifying code. That was the reason why in some of the Apple II programs, way back when, why they used self-modifying code. In the case of Microsoft, there are also pieces of self-modifying code, And the reason why they did that was to obfuscate, what the program does, so people cannot just disassemble a program and figure out how to defeat the copy protection features. So they were using self-modifying code to hide, how to defeat a particular program. So generally speaking, self-modifying code is a bad idea, like a really, really, really bad idea. So we don't want to do that. So instead of using self-modifying code, I somehow need to find out what is the first location that is safe for me to use as a counter. So how do I find that out? I can do this by hand, okay? In other words, I can look at the first instruction and say, yeah, this is going to take up 2 bytes. This is taking byte. Okay, let me count. Byte 01 is going to be here. Byte 2, byte 3, byte 4, byte 5. This is actually byte 6. So now I can say, I can safely change this 9 to a 6 to use a location that is not a part of the program itself. Okay? Did you guys just did you understand what I just did and how I did it? The attempt was to find the first location that is not a part of the program so I can use it as a counter. But to do that, I need to manually add up, all the bytes that I need to specify this program. It didn't seem too hard, right? I mean, would you want to do it by hand for something like this short? Sure, no problem, right? By the end of this semester, you'll be writing code that would probably get to maybe 100, 150 bytes or so. Would you want to count those by hand? Probably not, right? Because if you miscount by 1 byte, you might end up trashing the program itself, and then the program, not only does it not work, it'll be hard to explain why it's not working either. So you don't want to do this. You want the assembler to keep track of all of this stuff instead of having you to spend all the time to keep track of, oh, so how many bytes is this program using? Okay, so that's not a good use of your resources. So what you would do is to use a label. This is the definition of a label. I'm just using a very, kind of generic name of a label. L1. The name of a label can be anything that can be an identifier in the C++ program. So if it's okay to use as the name of a variable or the name of a function in C++, you can use that as the name of a label. The definition of a label always has a colon after the name of the label, and the definition of a label has to be the first thing on a line. You can have blank spaces before this, but you cannot have opcodes and other things in front of this. Is that okay? All right. So the way you define a label is not different from how you define a label in C++, because C++ actually you can define labels too. You can also have go-to statements. They're just, taboos in C++ programming, and that's why you may not have learned how to define a label in a C++ program. So the next thing is, now that we have defined a label, how do we refer to that label? And if I need to refer to that label, which line needs to be changed to refer to that label? So once again, this cup of water is going to be very important. Which line do I need to change to make use of label L1 if the objective is to say, I'll let the assembler figure out the first location to use as my counter? Line 2, very good. And I haven't even finished my cup of water. So you're exactly right, because on line 2, we are going to change the 6 to L1. So this way I can insert additional code between here, and I don't have to keep track of the counting anymore because the assembler is doing that trick. So the next question is, okay, now that we know how to define a label, now that we know the definition is on line 7, and we know how to reference a label, which is on line 2, is there a way for me to find out exactly how a label is defined? In other words, what is the integer that this particular label, which is a symbolic name, representing? So the answer is yes. There are a few ways to do it. The first way is to look into the Assemble tab. So when you look into the Assemble tab, you can see the definition of label L1 is on this line. And we can also see column V, which is addressed in decimal, is 6. So that means label L1 is just a symbolic name of the integer value of 6. That's all it is. So this 6 has no type, okay? Because in C and C++, you always have to worry about the type, okay? Is this a signed integer? Is this an unsigned integer? Or is it the address? And so on and so forth. In assembly language programming, there is no such thing as a type. 6 is just 6, okay? You can use it as an address. You can use it as a regular integer. It doesn't matter. Are we doing okay so far? Another way to look at the label definitions, especially if you have a longer program and you don't want to look at the Assemble tab, is to scroll all the way to symbol table. And in symbol table, this is what we call JSON, JSON, which is JavaScript Object Notation. This is internally how the assembler keeps track of the definition of labels. So I know it looks kind of more complex than it needs to be because the assembler needs to track all of these things. So we can see the name is label L1, and it is defined on line 6. And RPN is the one that you want to look at because RPN defines the actual value of label L1. So some of you are now probably thinking, why do you use RPN as the name of this property? Why don't you just say value as the name of the property? What does RPN stand for anyway? So I'm gonna finish my water as you guys try to look it up on you know, on your mobile device or using Google. What is RPN in this context? Should I pour a new cup of water? It is reversed Polish notation. Exactly. It is basically the same thing as a postfix notation or postfix expression. I have no idea why it's called reverse Polish notation because I didn't read the Wikipedia page, but it is reversed Polish notation. All right. So originally, this is kind of really interesting because a label can also be defined by a reverse Polish notation. I'm not going to get to that just yet in this class. Okay, so later on we can get there, but RPN stands for reversed Polish notation, which kind of gives you a clue of how else you can define a label, which is to use reverse Polish notation to say, hey, this label is that exactly. But right now, we're not using that definition. We are simply using the address of the line where the label is defined. So getting back to the program, going back to source here. So let's just say that I'm changing the program, okay? So I'm changing the program like this. I am going to cut and paste. Oh, okay, reverse. So let me do it one more time. Cut and paste like that. And I'm not sure whether and I put a no up here, okay, or some other instruction, okay. So right now I have just shifted all the bytes down a little bit. So what do you think is the new value of L1? It used to be 6. What should it be now? 7. Yep. So let's double check, make sure that is the case. We go to the Assemble tab, and sure enough, label L1 is now at location 7. Very good. So this is the reason why we use labels, is so that you don't have to worry about, oh, I just put in some code in between this place and this place. Now I have to recount all the bytes. Nope. You don't have to do any recounting. The assembler will do all the counting for you. Are we okay so far? Yes? All right. So remember what I did when I test ran this code, I was basically saying maybe I don't want to start with 0, 0. Maybe I want to start with a particular value. You can do that too. So the directive, this is not an instruction, it's called a directive. It's called byte. And then you can specify the constant that you want this location, this particular byte in RAM to start with. In other words, this is quote unquote, okay, the way you define an initialized global variable. Now, I have to emphasize that we have quote unquote because there's no direct match between the concept of a initialized global variable in C++ and the way we are doing it here. It simply has the effect of like defining a global variable. So now we can say, well, let's start with the value of, I don't know, 107, okay? So the byte 107 as a directive is telling the assembler, whatever this location turns out to be as we assemble the program, just stick the 8-bit representation of 107 to that location. That's all it says. Why 107? The assembler doesn't care. Okay? So now let's take a look at the assemble tab again, because the assemble tab is actually very useful if you want to understand what is going on, because now it says corresponding to that particular line, we have a byte of 6b at location 7, which is also where L1 as a label is marking. Why 6b? Well, the 6 is telling us how many 16s we have. So we have 6 times 16, which is 96. And then the 7, B, excuse me, the B is telling us 11 of ones. So now we are adding 96 and 11, and that does add up to 107 in decimal. So that's why we have 7B, because that, or 6B, sorry, we have 6B because that is the hexadecimal representation of the decimal value of 107. Are we good so far? All right. So let's go ahead and try out this program. Okay. So the thing about this class is um, the simulator. You cannot. I mean, you can probably break the simulator, but that's not going to break anything real. Okay. Your operating system, you will protect the simulator from doing any further damage to the rest of your system. Okay. So the whole idea is, if you're not sure, give it a try. If you want to get familiarized with the process, keep practicing, okay? Because that's why we have these tools, and it doesn't need much, just JavaScript. I mean, just Java to run it. Yes.
Where are you using L1 again?
L1 is here.
Yeah.
That's where the definition is.
And it just stays there? Like, you don't use it anywhere else?
Not in this program. I mean, I can change it if you. I mean, this program is a very simplistic program to show you how to reference and how to define a label. But then later on, we'll be using labels quite a bit because that is also how you can specify jump instructions. Where do we want to continue execution? Because that, in return, is how we implement control structures. Uh, okay, so this is a quick quiz. What is a control structure? What do I mean when I said control structure? Can you give me examples of control structures? More water? A loop is a control structure, and there are two types of loops. There's a pre-checking loop where the condition is checked first, and there's a post-checking loop, which means you perform one iteration, then you check the condition to see whether you should go back and perform another iteration. And there are also conditional statements. Those are also control structures where you have a single condition to decide which branch you should go to, the branch that corresponds to true, and also the branch that corresponds to false, okay, of the condition. You also have weird control structures like the switch statement, which is useful in some cases, but it's not technically really needed because you can always emulate a switch statement using a conditional statement. Well, I mean, granted, it's going to be a complex one, but you can do that. All right, but all of those require altering the execution path. which is also why labels are also going to be very important when we get to control structures. But right now, we are just saying, okay, where is the location that I can use as a counter? That's all we're trying to do now. All right. So we go to the RAM file because I want to run the program. So we go to File, we go to Download, CSV, and we'll call this one, counter 1, and then switch back to Logic Sim. Control R can reset the entire thing, so that saves you the one trip to the menu. And you right click, load image. This is counter1.csv. And once again, I'm going to just enable the ticks automatic. Tick, the program executes, and now we can see how. Uh-oh, uh-oh, did I make a mistake? 6B and all right. So let me check the code. It was 6B to begin with, and it remains as a 6B. Oh, something did not work. Um, because when I look at the source code, oh, that's okay. Now I know why you asked that question earlier. Because I forgot to change the 6 to a reference of L1. Okay, that was totally my fault because I forgot. That's why it changed location 6 instead of location 7. So the halt instruction itself got changed. Let me go back to the simulator and show you what I meant by that. So when you go here, you can see the halt instruction is supposed to be a 0-1. That got incremented to 0-2. And then you guys ask, but how come the program is still halted? And you look at the halt pin here, it is still 1. Well, that has to do with the microcode located at 020. That turns out to be also all zeros, just like 010. In other words, this is an unintended halt opcode. Is that okay? So that was my fault. I do apologize for that mistake, forgetting to change 6 to a reference to L1. So let's do this one more time. Go to the RAM file, download the CSV, and I'm going to keep the same name, counter1.csv, replace what I already have, switch to Logisim, Control R, reset the simulator, go to load image, and counter 1, there we go, and then Control K to start clocking. And this time we see how it correctly changes 6T to 6B. All right, so do we have any questions at this point? Because that is pretty much all you need to know for today's lab. So we're okay here? All right. All right, so I'm going to take row. I know it's a time-consuming thing, and we really should not be spending too much time with taking row and stuff like that. But it is still important because I really want people to, well, at least I want to know if people are not showing up. I need to know. So we'll go ahead and do the row taking thing. So give me a second. You cannot see it just yet. When I say refresh, go ahead and refresh at that point. All right, so today is the 27th. And I'm going to change the nature of how this is done. So I'm going to require an access code. What should I use as an access code for today? Increment. So increment is the access code. Let me find a pen to write it on the whiteboard. Oh, that doesn't work. And that also does not work. That barely works. Increment. No, that doesn't work. All right, so 3 out. There's only 1 left. This one looks like it's going to work because it's heavy. And it's still not working. Wow. We are completely out. Oh, wait, there's one more. It's also green. Oh, this one is okay. All right, so there we go. All right, so I'm also going to change the nature of the question so that it just says, are you in class today? So let me go ahead and do that. Are you in class today? And it's going to be true, false. And true is the right answer, false is the wrong answer. Okay. I have to remember to click this update question because there are many times I forget to click update question. And even if I save the entire quiz, it's not going to take the new quiz. So we'll make it due in 20 minutes, 10:20 a.m. That gives you plenty of time. Save and publish. So if you refresh now, you should be able to get to it. More water. I'm not sure how many of you understand the reference to initial D for the cup of water.
I mean, it's not one thing. No, it's not worth points. No, it's not.
All right, so I think most of you are done with the road taking activity. So what I'll do now is to kind of give you a heads up of what's going to happen next week, okay? Because you might need some, I would say, preparation for what we're going to do next week. So this is the announcement that I sent out earlier today. So what we're going to do next week is to get into the more complex instructions. CMP is compare. JCI is jump if and only if the carry flag is 1. And then JMPI is just an unconditional branch instruction. So the first thing okay, what if I just give you the first line in this announcement, how are you going to study, quote unquote, over the weekend? Where do you go? The opcode sheet. Very good. Okay, so the opcode sheet or the opcode table is one of the resources that you should look into. So you want to look into um, at least column B, column C, and column D of each of these instructions. So you want to find out what compare really is and what is JCI, at least based on the description, and what is JMPI based on the description. After you read those particular rows, there are 3 rows that you need to read, then what do you do? How do you experiment with these instructions just based on the description in the opcode table? So I would even go to the opcode table itself and give you an idea of what each one is, and you can test each one individually. I would suggest that you work with compare first. So this is compare. Doesn't look too complicated, does it? Because all it does is it wants you to tell it which 2 registers to use. They can be the same one, but if you use the same one, it's not going to be very interesting. So I would say register A and register B or something like that. And what it's going to do is it will just perform the subtraction, but it doesn't do anything with the difference. In other words, after the subtraction, the difference is tossed away. It is simply like, I don't care about the difference. So you go like, then why perform the subtraction? Because you're not using the result of the subtraction. As it turns out, it does affect all the flags that we have talked about in binary comparison. Okay, so that means one of the things you need to look into is logisim itself. So you need to look into logisim, particularly go into the ALU and find out how we define all of those flags. So you want to track, what about the subtractor? This is the subtractor, right? So the subtractor has one borrow bit output that goes into this multiplexer. Nope, I take it back. The borrowed bit does not go into this multiplexer, but it does go into another multiplexer, which is this one here. And this multiplexer output is C out, and C out becomes bit 0 of this particular splitter, which goes into flags output. Okay, so that's the first thing that is kind of important. And then the other thing is, well, hold on a second here. I can see a Z flag here. What is that? How is the Z flag defined? I see a sign flag here. How is that defined? There's an overflow flag here. How is that defined? So you might want to track down every single one of these and relate what you see in the ALU to binary comparison. Because when we talked about binary comparison, we talked about the overall borrow bit, which basically becomes the quote-unquote carry bit, because those two are basically the same thing from the perspective of the ALU. We talked about the sign flag, which is the most significant bit of of the difference, the result of the subtraction. Okay, that's the sign flag. We talked about the overflow flag, right? So how do we compute the overflow flag in the subtraction? We look at the most significant bits of the minuend, the subtrahend, and the difference, right? Okay, and then we have the L flag, right? So what is the L flag? The L flag is this thing here. It is the exclusive OR between the sign flag and the overflow flag. Okay, so we have exactly the same thing here as what we talked about in binary comparison, except all of those things are now implemented using logic gates. So if you go back up just a little bit here, you can see the overflow is computed here. So in the subtraction, this is the way we compute overflow in the subtraction, because this is how we compute overflow in an addition, but we're only concerned about subtraction at this point, and this is how we do it. So now you have to look at the input into those AND gates, and you ask, where is S1 coming from? What is S2 coming from? And what is S out coming from? So once you locate those, which is all the way up here, so S1 turns out to be just bit 7 of input 1. S2 turns out to be just bit 7 of input 2. And then S out turns out to be just the output, bit 7 of whatever the result is. So now we have all the sign flags, right? We have the sign flags of the minuend, the subtrahend, and also the difference. And all of those are combined in this particular subcircuit here. And this subcircuit is saying, okay, let's find out what it's doing. The negation of the most significant bit of the minuend and the most significant bit of the subtrahend and the most significant bit of the difference. Not X, Y, D. And this is an OR. The most significant bit of the minuend, X, the negated version of the most significant bit of the subtrahend, which is Y, and the negation of the most significant bit of the difference. So this is something that, I just said it, right? But you might want to do this on your own to relate what we learned in binary subtraction and see how all of those things are implemented inside the ALU. Well, it's useless if nobody cares about the flags. So the question is, with all of these flags here, so we have the carry or the borrow flag, depending on whether the previous operation was an add or subtract. We have a zero flag. What is the zero flag? So you want to look up the zero flag. It's also defined here. This is the zero flag. What is it doing? What do you think is the name of this particular gate? The bubble means a negation, but if you ignore the bubble, okay, if you ignore the bubble, what is the gate without the bubble? It's a okay. We only have like 3 major gates that we talk about in this class. We have AND, we have OR, we have exclusive OR. So which one is it without the bubble at the end? It's an OR. Okay. So with the bubble, what is it? It's a negated OR, which is also known as a NOR gate. Okay, it's a negated OR gate. And what is it ORing? It's ORing each individual bit coming from the output of this multiplexer. So if I were to ask you, when do you think the Z flag, which is the output of this entire gate, when is it going to be a 1? How would you describe when the Z flag is going to be a 1? Okay, so how do we go about doing this? We go reverse, right? We reverse the direction. We want this to be a 1, but it is negated, which means coming out of the regular OR gate has to be a 0. So the question is, how do you make the output of an OR gate a 0 or make it false? All of the inputs need to be, well, the inputs need to be, this is a regular OR gate, okay? We're talking about an OR gate. How do we make the output of an OR gate false? In other words, I'm asking, bit 0 or bit 1 or bit 2 or bit 3 or bit 4 or bit 5 or bit 6 or bit 7 needs to be 0. How can I make that happen? All of those bits need to be zeros. Very good. Okay. So the only time the Z flag is a 1 is when all the inputs to the NOR gate are zeros. And hence the name, the zero flag. That's why it's called the Z flag, because it is representing when the output is a 0. Whatever computation you just did ended up with a 0. That's what the zero flag is. Okay? All right. So with all of these flags, okay, let me just kind of scroll down again to the 5 flags that is important to the processor. So we have the carry flag, we have the 0 flag, we have the sign flag of the result of the operation, and then we have the overflow flag, which is only applicable after an add or subtract. And then we have the L flag, which is also only going to make sense after a subtract instruction. All of those are combined into this output. And where is that output going? So let's go check out where the output is going from the ALU. So we are talking about this particular output of the ALU. It goes into, oh, wait, is that correct? Nope, take it back. It is the red wire. So the output of the flags goes into the input of the flags register. So that means there is a very special mechanism in the processor that pays attention to all the flags and remember the flags after a subtract or a compare instruction. So even though the compare instruction, if I go back to the browser, even though the compare instruction looks like it's doing something and it's pointless because we're only performing the subtraction and not storing, not doing anything with the difference, it will still change all of those flags. So it's going to change the borrow flag, which is also known as the carry flag. They're the same. It will change potentially the Z flag. It will change the sign flag, the overflow, and also the L flag. Is that okay? So all of those flags are going to be remembered somewhere within the processor. So the next question that you'll be thinking about is, so who's going to use those flags? I mean, just because we're going to change it doesn't mean it's going to be useful. If none of the other instruction is using these flags, then why are we tracking those things, right? So that is when we get to the JCI instruction. In fact, it is a whole family of instructions that would do something um, differently depending on the flags. So we are talking about this entire family of instructions here. So we have JLI, JOI, JSI, JCI, and JZI. So I'm gonna pick one of them because the other ones are kind of the same thing. So we'll just pick one of them, which is JCI. So what does the JCI instruction do? I mean, according to this role, how is it described? If you look at column D, it says jump to a destination that is specified by the I operand if and only if the carry flag is a 1. I did not specify when it is a 1 because if you look at C or the flag as a Boolean, that means it's already just true or false. Is that okay? All right. But when you look at column C, it looks even more mysterious because when you look at column C, which describes the actual mechanism that, that gets the job done, what is it saying? It's using a ternary operator, because we have a question mark and a colon. It's using a ternary expression. It says if C is true, then PC, the program counter, is going to be updated by whatever the program counter itself is pointing to. Okay, that looks kind of strange. What if C is false? What if C is 0? Then we simply increment the program counter. That is how decisions are made when you write programs in assembly. It pays attention to one of the 5 flags, and it says, if and only if that flag is a 1, I will go to the location that you tell me to go to using the only operand of the instruction. Otherwise, what do? I simply said, okay, let's just pretend this instruction is not even here. I'm just going to continue with whatever is next to this instruction, whatever is following this instruction. This is the only way you can do branching when you write programs in assembly language. And we are going to get to a point where we can do, like factorial, well, maybe not factorial, but we can do Fibonacci, recursive function calls where you have to say, am I supposed to go for another recursion? That's a decision, right? It's going to be done using these instructions. We can also do the Tower of Hanoi. We can do loops. We can do all kinds of stuff. And they're all being done, all the decisions, all the places where you have a branch, they're all done by the conditional branch instructions, which are these 5 instructions from JLI all the way down to JZI. These are the mechanisms to make decisions and branch. Is that okay? Aren't you guys looking forward to the next 5 weeks? Because we will be converting C programs into assembly language programs, and we'll be looking at all the loops, all the conditional statements, nested or otherwise, and we'll convert everything, all the control structures, we'll be utilizing the jump instructions. Now, of course, nothing is complete, okay, without the unconditional branch instruction. So there's a jmpi instruction, which is basically saying, I'm just going to I'm just going to continue execution where you tell me to, okay? So when you look at column B, the format of a jmpi instruction in terms of the mnemonic is simply jmpi followed by where you want it to go. This is a great place to use labels because now you can use labels in your program to bookmark places and go like, I want you to continue execution over here. So you define the label where you want to continue execution, and then in the jmpi instruction, you refer to that label. So this way, you don't have to keep track of the counting of the bytes and go like, oh, what is the number of that location again? I have to re-add all the numbers. Nope. Leave it to the assembler to do all the adding. If you look at column D, the jump instruction simply says jump with immediate destination, which means you specify the destination where you want to go using the immediate operand. So that's pretty easy to understand. But when you look at column C, it is a little mysterious, right? It says PC gets whatever PC is pointing to. Haven't you seen something like that, about using whatever the program counter is pointing to as to give you a value, to do something about that value? We did that just today. So which instruction did we use today that makes use of the byte that the program counter is pointing to as a part of the execution of the instruction? LDI. Okay, so the LDI instruction also has a component like this, except we are not storing that into the program counter. We're storing that into one of the 4 registers in the register bank. Okay. So what are you guys going to do over the weekend? Given that I'm giving you a little head start already of what instructions we'll be talking about, but I did not go through Logisim edge by edge to show you how this is done, right? So that would be something that you can do over the weekend, is to write very simple programs, okay? I can give you a few examples. Okay, the first simple program that you can write is just something like this. Okay, I know it doesn't look like much, but give it a no op instruction here, jmpi to location 0. So I would suggest, okay, play with this program. Okay, single edge through the entire program. Pay attention. The no op instruction is not going to be a whole lot of fun because it's no operation, but the execution of the jump instruction is something that's going to be interesting. Okay, so I would try this one. This is the first one. The next program that I would suggest you guys to try is to load values into register A and register B. So you're intentionally setting the carry flag. So, so to do this, um, register A has to be less than register B. So I can have 3 here, and I can have a 4 here. And then you do a JCI to location L1, and then perform an unconditional branch to location L2. L1 is defined here as a halt instruction. L2 is location here, which is also a halt instruction. So when you test run this program, which halt instruction should I end up at? Remember, compare is subtracting the second operand from the first. Oh, I forgot about the compare instruction. Okay, never mind. Sorry, that was my fault. I forgot. Okay, Control X and Control V. I need a compare instruction here. There we go. So this is doing A minus B and change the flags. And this instruction says if and only if the borrow flag, because borrow and carry are the same flag, if and only if the carry flag is a 1, continue execution at L1. And if not, continue execution with whatever is right next to it or following the JCI instruction. So what do you think is the behavior of this program, just based on what I described? Which halt instruction should I end up at? I need a bigger water bottle now. All right, so this is something you can do, okay? Give it a try, okay? Because this particular program intentionally sets the carry flag, which means the carry flag is going to be a 1, which also means the JCI instruction will indeed branch to location L1. So that means the halt instruction of line 7 is where the program is going to be stuck at. Next question. How do I change this program so it's going to be stuck at the halt instruction of line 9? You can change one of the values of A and B. In other words, you change one of the 2 LDI instructions. And then you can force the carry flag to be a 0 after the compare instruction. Then it's going to end up at location L2. All right? So you can basically just play with this program. Change the constants with the LDI instructions a little bit and see how the behavior of the program changes. But more importantly, if you don't single edge through the entire program, I would at least single edge through the JCI instruction and also the single edge through the jmpi instruction. This way you understand how the internal pathways of the processor is being configured in order for that to happen. So those would be the highly recommended activities of, for this class. This is basically studying for this class. I mean, studying for this class is not just reading a lot of material. It is actually, just trying out different things. Look into the mechanism, and if you're looking for the reading material, I can show you where the reading material is. That is a reading material because it is already open sourced. It's just a matter of tracking things down to figure out how it is done. All right, so this is all done. The lecture is over unless you guys have questions. So I'm going to open up the lab activity for today, which is going to have LDI, the labels, and so on. Oh, that's the wrong class. And let me see, where's my correct class? Right there. Yep, that's the right one. All right, So today's lab is LD, ST, and LDI. And if I remember correctly, the access code is LDI itself. Let me just double check. Shuffle answers. Yeah, sure. It probably doesn't matter in this particular one. 12 p.m. is when the answers will show. The access code is indeed LDI, so I'm going to write it on the whiteboard. LDI, or lowercase. And it's going to be due at noontime. Save and publish. So if you refresh now, you should be able to get into today's lab. By the way, this is a 40-ounce water bottle, and I think I'm close to emptying out the entire thing. All right, so I'm going to stop the recording.